In this video, I want to demonstrate how to set up a differential equation. And I'm going to use a very common system that is fairly well known to chemical engineers to demonstrate one way to do this. So what we're talking about here is a heat exchanger. So a heat exchanger is a unit in which two fluid streams flow through it. Let's name these streams stream 2 and stream 1. And let's assume that we have a fluid flowing at a flow rate F2, a density ρ2, and a heat capacity Cp2 into stream 2, and likewise we have a well-defined flow rate, density, and heat capacity coming into stream 1. Furthermore, these streams are going to have different temperatures. The purpose of a heat exchanger is to take energy from the hot stream and transfer it to the cold stream. Let's assume that stream 2 is the hot stream. And if we define a coordinate system, so this is x starting at 0 at the entrance of the heat exchanger and ending at L, where L is the length of the heat exchanger, we would expect behavior that looks like this. So T versus X. If we assume that, let's use this to be stream 2's temperature, T2, and a different color to be stream 1's temperature, then we expect the hot stream, stream 2, to transfer energy to stream 1 so that if the reactor is long enough, the two streams should come to the same temperature. So in other words, you have heat transferring in this direction, presumably because the wall that separates the two streams is not a good insulator. So notice that temperature changes continuously with position. And so in order to do this, we need to formulate, in order to calculate temperature as a function of position, we need to formulate differential equations that will allow us to calculate T2 as a function of x and T1 as a function of x, with the initial condition that T2 0 equals T2 in, T1 0 equals T1 in. Now in this video, we're not going to focus on how to solve the differential equation. Our goal here is to set it up. And there's a couple things we need to do in order to establish, the right set of assumptions. So let me just list assumptions. I should mention that these assumptions are not really meant to be accurate, but they're meant to keep things simple enough to illustrate how we go through the process of setting up a differential equation. So the first one is that fluid properties are constant. In general, temperature and heat capacity should actually change, density and heat capacity should change with the change in temperature of each fluid. But for simplicity, I'm just going to assume that those are constant. And also, for heat transfer, I'm going to assume that we can use Newton's law of cooling. So I'm just going to say heat transfer per unit area. What I mean is that at any given position within this reactor, you have a certain surface area of contact that would allow heat to transfer. And I'm going to just say that it's going to be H, some constant heat transfer coefficient, times some surface area of contact times T2 minus T1. So I'm using a heat transfer coefficient, which I'm assuming to be constant, and that'll give me a simple expression for how to compute energy transfer across the interface. So notice that what we're assuming here is that energy transfer or heat transfer is proportional to the temperature difference. Hopefully that makes sense to you. And the third assumption is that internal energy of a fluid, right? So when heat is transferred to a fluid, what it effectively does is change that fluid's temperature. And I'm going to assume that the energy of a fluid is just going to be rho Cp times T minus T ref. And ref is just some reference temperature. In fact, we'll see that it's not actually that important. You could say, for example, that the reference temperature is just the temperature of one of the inlet streams. What's important is that whatever the reference temperature is, we don't want there to be a phase transition. Say, we don't want the fluid to evaporate or freeze or melt between the temperature of interest and the reference temperature, so that the assumption that the density and heat capacity of that fluid is constant. Again, these are details that I'm going to leave to other courses like transport kinetics, thermodynamics, to really describe in detail. My purpose here is really just to show you a simple example of setting up a differential equation. So in order to do this, I want to use simple assumptions. Now, the way you treat a differential equation in which temperature varies continuously is to actually do a differential balance. Okay, so what I'm going to do is I'm just going to choose some arbitrary position x and x plus delta x. Okay, I am also going to choose only one of my channels. So let's choose T2. And delta x is going to be small enough that we can assume that the temperature T2 does not vary across that very small increment of x. So we're looking at a very small sliver. So what actually happens? So you have fluid flowing in, and if you want, so we're going to do both a material and an energy balance on this control volume. You have fluid flowing out, and you have heat transfer from stream 1, in which only energy enters across that boundary. So the streams do not mix. And what we will do is we'll balance energy, and then we'll take the limit as delta x goes to 0 and apply the definition of a derivative in order to get a differential equation. So let me step back a minute and talk about the definition of a derivative. So if I have a function, and that function depends on x, let me just draw something. And I have the following situation. I know the function value at x. So this right here is going to have value f of x. Actually, let's draw it this way. F of x. And then I look at the same function, but evaluate it at x plus delta x. Remember that the derivative is the slope of the tangent line. So as I'm drawing it right now, it's not really a tangent line that I'm drawing. It's actually more like a secant line because it's connecting 2 points at f or x comma f of x and x plus delta x comma f of x plus delta x. It's connecting 2 points to the line, but as I take the limit as delta x goes to 0, this becomes the tangent line. So f of x plus delta x minus f of x divided by delta x. And in fact, this is the definition of f prime of x. So the derivative is the slope of the tangent line that you get by taking the limit as delta x goes to 0. So remember that when we actually do this differential balance, we're going to apply this to actually calculate differential equations in terms of the temperatures. So let's come back to our balance. So this one, I'm going to start with a material balance on stream 2. So if I have a flow rate F2, and presumably that has units of volume per time, well, let's say liters per hour, and I have a certain density, then I can calculate in some increment of time what amount of fluid would enter my control volume. I can do the same thing here. And remember that I'm making the assumption that F2 is constant and so is rho 2. So it turns out that this balance is not all that interesting, but let's write it out anyway. So remember that this is an increment delta x along the flow channel. So perhaps the most important equation in chemical engineering is in minus out plus generation minus consumption equals 0. So balance equation. So the input is, so let's do things in terms of rates of input. So if I say rho F2, and by the way, I probably need some sort of cross-sectional area because remember, let's look at the units. This is volume per time. This is density, so if you take rho times F, you will get mass per unit time. And actually, I guess you don't need a cross-sectional area. Well, fine. So this occurs at X. The output, rho F2, occurs at X plus delta X. There is no generation of mass in this problem, and there's no consumption of mass. This equals 0. So for the moment, we were going to, this really just evaluates to 0 equals 0. So it's not interesting. But just as an exercise, let's just relax the assumption that F2 is constant. We'll find that the math actually, if we assume rho 2 is constant, it'll actually force us to assume that F2 is constant as well. So let me do that. So if I say rho 2, which is a constant, times F2 evaluated at x minus F2 at x plus delta x equals 0, I can actually divide through by rho 2. I can also just multiply by -1, and I get F2 at x plus delta x minus F2 at x equals 0. I can also divide by delta x, because it's just 0 on the other side. I can take the limit as delta x goes to 0. And then this, by definition, is just df2 dx equals 0. So this is a differential equation, right? df2 dx equals 0. It's actually very easy to see what the solution to this differential equation is. And that solution is just that F2 equals a constant. We could call it F2 in, the input flow rate of stream 2. But really, it's just an acknowledgement that if density is a constant for this system, then so is flow rate. So we relaxed the assumption that flow rate was constant, and the math forced us to do this. So let's now do a more complicated balance. Let's actually go back to this control volume and actually do an energy balance. So remember again, this is x. This is x plus delta x. So we have energy flowing in. Because this is stream 2, we have the internal energy of the fluid, right? So the internal energy is going to be rho 2 Cp2 times T2 minus Tref. And this is going to occur at x. You're going to have the same equation, rho 2 Cp2 T2 minus Tref, occurring at x plus delta x. And then also remember that you have an input of energy. You could call it, actually, let's call it an output. I think we were assuming that the stream 2 was the hot stream. So this is going to be H times some cross-section, or not cross-section, some surface area of contact. And remember that if we're talking about a continuous channel, we can't actually describe surface area of contact in absolute terms. It would actually just be surface area of contact per unit delta x. So the actual surface area would be A sub s delta x. And then this would be T2 minus T1. And so if we now balance the energy, right? So let's go back to our favorite equation, in minus out plus generation minus consumption equals 0. Again, by the way, this is a steady state assumption. In other words, no accumulation. Then what we are going to get here is, again, remember that we're balancing rates. So this is going to be energy input per unit time. And so, by the way, this is a mistake. I have to actually multiply by F2. So the input rho Cp F2 T2 minus Tref evaluated x minus rho Cp, these are for stream 2, F2 T2 minus Tref evaluated x plus delta x. That's the input minus the output. The generation is 0, the consumption is 0, and the accumulation is 0. And, sorry, I forgot one of the input terms. So we have, actually, sorry, I forgot an output term. This is the term I forgot. So this is going to be minus, maybe I'll move it over here, minus H A sub S delta X T2 minus T1. And so let's actually collect some terms. And what we're going to look for is the definition of the derivative as we take the limit as delta x goes to 0. So rearranging this, I'm going to say rho 2 CP2 F2 times T2 minus Tref evaluated at x minus T2 minus Tref evaluated at x plus delta x is going to equal H A sub s delta x T2 minus T1. Now notice something. Tref is a constant, right? I said I could choose it as long as I choose something that maintains the assumption that CP is constant. And if I do that, this constant should not depend on x. So Tref evaluated at x would be the same as Tref evaluated at x plus delta x. So remember I said that in the end our choice doesn't matter. In this case, we can just cross these out. Again, assuming that we can choose some Tref, whatever it is, that maintains the assumption that density and heat capacity are constant over the temperature range we're considering. Again, this is a simple analysis. And so what we can do is simplify this to T2 at x plus delta x minus T2 at x. I'm going to divide by delta x. And this is going to equal H A sub s over rho 2 CP2 F2. And this is going to be T1 minus T2. So notice that I changed the sign here, right? So I put the x plus delta x term in front. There's a negative sign there. In order to rationalize the negative sign change, I have to actually switch the order of the temperatures here to make everything work out. And now if I take the limit, delta x goes to 0, what I'm going to get is dt2 dx equals, by the way, I don't feel like writing this out. I'm just going to call this alpha 2, some constant in my system. Okay, so this is our differential equation for T2 as a function of x. Let's do a little physical reality check here. So we made the assumption that stream 2 is hotter than stream 1. So if that's the case, then dt2 dx should be negative. T2 is going down as you move across the heat exchanger. So let's see if that makes sense. Okay, so when we assumed that T2 was the hot stream, we in effect assumed that this is a negative quantity, right? So that means alpha should be positive, again, because these constants were all defined to be positive. That means that this is actually less than 0. So in fact, that worked. And by the way, the assumption wasn't necessary. So let's make the opposite assumption. Let's actually assume that T1 is higher than T2, that stream 1 is the hot stream. Well, all that's going to do is result in this being positive rather than negative. And remember here, I assumed this was an output. But if T1 is bigger than T2, then it's a negative output, right? This term is negative. So it turns out not to matter. In fact, if I had made the assumption that stream 1 was the hot stream, then it would have made sense for me to treat this as an input. But if that's the case, I would have actually had to put T1 minus T2 to describe this term. And so in the end, I would have gotten the same result. And so for good measure, let's also now do a different control volume. Let's consider the same region, but in the other stream. So now let's look at stream 1. So this should look exactly the same. I'm just going to do an energy balance. I'm going to skip the material balance. This is x. This is x plus delta x. And I have energy flowing in terms of internal energy. So I have rho 1 CP1 T1 minus T ref. I have energy flowing out. So this is going to be H A sub S delta X. So the surface area of contact T2 minus T1. So what we're assuming here is that the driving force for energy transfer out is the temperature difference T2 minus T1. And just like we found before, even though we're thinking about T2 as being the hotter stream, we'll actually get the same equation if we later assume that stream 1 is hotter. And so the output is going to be the same internal energy of the fluid evaluated at x plus delta x, so rho 1 CP1 T1 minus T ref. And so the equation in minus out plus generation minus consumption equals 0, no accumulation. We're doing steady state balance. Let's just right off the bat write those as 0. So we need the inputs and the outputs. Oh, by the way, I didn't mean to draw it like this. I meant to draw it like this. So that's an input coming from stream 2. So once again, I forgot the flow rates. So rho CP F T1 minus T ref evaluated x plus the other input is going to be H A sub S delta x T2 minus T1. The output is going to be rho 1 CP1 F1 T1 minus T ref evaluated x plus delta x. And this is going to equal 0. So let's rearrange things just as we did before. So again, the T refs will cancel because they don't actually depend on position. And we're going to get T1 at x plus delta x minus T1 at x is going to equal H A sub S T2 minus T1. We're going to divide through by delta x, or take the limit as delta x goes to 0. And this is going to be a HAS over rho 1 CP1 F1. And this is going to be d by dt of T1, or dx, I mean. So this comes out to alpha 1 T2 minus T1. So the system of equations is going to be we actually get a system of two coupled differential equations. That's supposed to be a derivative. So that was our purpose in this video, to show how a differential balance can be used to derive a differential equation. I hope that was helpful. I want to point out one last thing, and that is what happens if the direction of a stream changes. So I'm going to use green lines. So we also, in chemical engineering, consider countercurrent flow. So if I were to change this flow direction, what would actually change? So the balance on stream 2 would actually not change at all, right? Because it only really depends on the temperature at that position. It doesn't actually depend on the flow direction. What does change is this. When you actually look, wrong stream. When you look at the direction of the fluid flow for the balance on stream 1, you change which is an input and which is an output, right? So in other words, this term, evaluate x plus delta x, is actually the input term. So that is actually going to make it positive. And this term, which is evaluated at x, is now an output, and that'll make that negative. So the net effect is that this will have a negative sign. So if you change the fluid flow direction, you get a very similar looking equation, except in the end, you have T1 minus T2 instead of T2 minus T1.